Hi, this is Dharani Murali and you are watching part 1 of ACE Math series, in which today we are going to start with the theory part of exercise 1.2. In last video, we discussed about the introduction part of this first chapter, and then we also discussed about the fundamental theorem of arithmetic and we solved exercise 1.1. Now, we are going to start with the exercise 1.2 theory part. If you are new to this channel, do subscribe this and click the bell icon so that you don't miss any notifications. Now let's start with the theorem. Let P be a prime number. If P divides A square, then P divides A. This is what is the part we are going to prove. We will take P divides A square as given and we will prove P divides A, where the conditions are P be a prime number and A is a positive integer. Keeping these two things in mind, and we will take the given condition as P divides A square and we will prove that P divides A. Now let's start with the proof. We will proceed it in the form like, first we will consider, let the prime factorization of A be A is equal to P1, P2 up to Pn. This is product P1 into P2 into ... up to Pn. As we saw in the fundamental theorem of arithmetic, any composite number can be represented as product of primes. So here given is A is a positive integer. So we are considering it as a number and we are representing it as product of primes, where P1, P2, Pn are primes which are not necessarily distinct. Means P1, P2 can also be same numbers, like if we take 2 into 2 into 3, it will be 12. So here P1 will be 2, P2 will be 2 and P3 will be 3, like this. 12 is equal to 2 into 2 into 3. So we will take P1, P2, P3, then these two are same numbers. Here P1 and P2 are not distinct. That is what they are saying. Like we can take A is equal to P1, P2 up to Pn, where P1 to Pn are prime numbers and these are not necessarily distinct. Now let's take A square, as we know that P divides A square is the given condition. First we will find A square. A square is equal to A into A, where P1 into P2 up to Pn. This product is nothing but A. So we are taking A square is equal to A into A. So we will get A square is equal to P1 square into P2 square into ... up to Pn square. So we are given that P divides A square. Okay. Then P must be a prime factor of A square, because this is what was the uniqueness part of the fundamental theorem of arithmetic which we saw in the previous video. Like fundamental theorem of arithmetic states that any composite number can be represented as product of its primes, and this prime factorization is unique for every composite number except for the order in which they occur. This they are saying like prime factorization is unique for a particular composite number, right? So this one we will say it like uniqueness part of the fundamental theorem. By this, P is one of the prime factor of A square and we know that A square is equal to P1 square into P2 square into product up to Pn square. So by the uniqueness part, P must be one of the numbers from P1, P2 up to Pn, either P1 or P2 or P3 or from up to Pn. P should be one of the numbers of P1, P2 up to Pn. This we get from the uniqueness part of the fundamental theorem. Now just we have proved that P is one among the prime factors P1, P2 up to Pn. Then we know A is equal to P1, P2 ... or product up to Pn. So if P is one among these numbers, then P divides A. This is what we had to prove in this theorem, and we have proved. Now we will move on to the next topic, in which we are going to discuss about the proof by contradiction method. Proof by contradiction. This is a method in which in the proof we will consider the exactly opposite to that of the required result to be correct, and in this process eventually we will get a contradicting result or which will not match our assumption. So we will say that this kind of contradiction has arisen because of the wrong or incorrect assumption which we have made in the beginning of the proof. So since we have considered the exactly opposite condition to that of the required result, we will say that because of this contradiction our assumption is wrong and the required result is correct. By this way eventually we will prove the required result. This type of proof is called proof by contradiction method, or simply proof by contradiction. Majorly now we are going to use this method for proving irrational numbers. In the upcoming exercise 1.2, we will get certain numbers as questions which we will have to prove as irrational. So in the first step we will assume it to be rational, then we will make the conditions or take the conditions that will be suitable for the rational numbers, and we will get a contradicting result in the mid of the proof. So we will say that the required or the given number was irrational. So now let's get into the exercise 1.2 first question. In the first question it is asked that prove that root 5 is irrational. So just now we learnt about the proof by contradiction method. In that I have also said for proving irrational numbers we will use this method. So this question also you see it is asked that prove that root 5 is irrational. So this is a irrational proof. Here we will use proof by contradiction method. So now we have to prove root 5 is irrational. So we are going to assume root 5 to be rational. Rational numbers are exactly opposite to that of the irrational numbers. So we will assume that root 5 is rational. Also we know what rational numbers are. Rational numbers are, we can say that any number which can be represented in the form of a by b, where b is not equal to 0. That is a number which can be represented as ratio of integers are called rational numbers. So if we consider root 5 as rational, then we can also say that root 5 can be expressed in the form of a by b, where a and b are integers and b is not equal to 0. That is what we are saying here. If root 5 is irrational, then we can find integers a and b such that root 5 is equal to a by b, where b is not equal to 0. So now we will also take such conditions like if a and b have any common factor, then we will divide both of them by the common factor and we will make a and b co-primes. So what co-primes are? If we say a and b are co-primes, then a and b have only one number 1 as common factor and it does not have any other common factors. Okay, so any two numbers having only 1 as the common factor and which does not have any other number as the common factor are called co-primes. So now we are just imagining like a and b have some common factor and we are dividing a and b by the common factor and we make them co-primes. So for now root 5 is equal to a by b and a and b are co-primes. So this condition we will just rearrange this and write like b into root 5 is equal to a. We are just rearranging the condition which we have taken and we make it as equation 1. Now what we are going to do is that we will square this equation 1 on both the sides. Generally we can square, we can divide any number to rearrange or to get a new form of the particular equation. But whatever mathematical operation or thing we are performing, we have to do it on both sides of the equal to sign. That is what we are doing here. Like we are squaring on both the sides of this equation, we will get b root 5 the whole square equal to a square. when we square this and rearrange, we will get it like root 5 into root 5, 5 b power 2 b square. So 5b square equal to a square. Now from this condition we can say that 5 divides a square, or a square is divisible by 5. Here we are saying a square is divisible by 5. So just now we have proved a theorem which stated that if p is a prime number and p divides a square, then p divides a. Now we are saying that a square is divisible by 5, then by the theorem we can also say that a is also divisible by 5, or we can put it in other words like if 5 divides a square, then 5 also divides a. If we say that 5 divides a, then we can also frame a condition like a is equal to 5c. Since we say that a is divisible by 5, then we can say that a is equal to 5c, where c is some integer. So now we will list out all the equations whichever we have made in the process, and now we have got this equation. When we say that 5 divides a, now we are going to square this equation 3 on both the sides, then we will get a square is equal to 25c square. Now you see a square is present in both equation 2 and equation 4. So for a square we are going to substitute 5b square in the equation 4. So a square equal to 25c square. In place of a square, if we substitute 5b square, we get 5b square equal to 25c square. Here 5 is common in both the sides, so we can cancel like 5 into 5, 25. So b square is equal to 5c square. Now from this condition we can say that 5 divides b square. Then by the theorem we can also say that 5 divides b. So see, from this equation we can say that 5 divides a, and from this equation we can say that 5 divides b. Now it means that 5 is a common factor for both a and b. But if you remember, in the initial step we did that we divided any common factor from a and b, and we said a and b are co-primes. But here we are getting 5 is a common factor for a and b, which is a contradiction. And this contradiction has arisen because we have made the incorrect assumption that root 5 is rational. So we will say root 5 is irrational. Now we say that therefore this is the proper way of giving the proof. Like then a and b have at least 5 as the common factor. This is a contradiction to the fact that a and b are co-primes. This contradiction has arisen due to the incorrect assumption. So we prove that root 5 is irrational. By this way we will get the proof for this question. Now let's move on to the second question. In second question it is asked that prove that 3 plus root 2 root 5 is irrational. So as usual we are going to start with the proof by contradiction method. Let us assume 3 plus 2 root 5 is rational. So again, when it comes to the rational number, we can take a and b, or we can find two numbers a and b as co-primes such that b not equal to 0, and this rational number or the number which we are considering it to be rational can be expressed as the ratio of integers. That is 3 plus 2 root 5 equal to a by b, which on rearranging we can get it like 3 is positive here. When we take this 3 to the other side of the equal to, it becomes minus 3, a by b minus 3. Now again this 2 we will be taking to that side, which has come to the denominator of the other side of the equal to. What we are actually doing in these steps is that we are isolating the root 5 number. Why we are doing this? We will see in the next step. Now this 2 is common denominator for both these terms. So we can write root 5 is equal to a by 2b minus 3 by 2. Now on taking LCM, we can get root 5 is equal to a minus 3b by 2b. So here you see root 5 is represented as ratio of integers. This a minus 3b by 2b can be called as ratio of integers because a and b are integers here. So if the right hand side part of an equation is rational, then the left hand side will also be rational. But we know that root 5 is irrational. In this question, in previous question, single root values we proved as irrational. But here you see, these are combination of numbers. Here we should prove 3 plus 2 root 5 as irrational. So we can take it in the way that we already know root 5 is irrational. That is why we are saying by this step we are getting it like root 5 is rational. Since we already know that root 5 is irrational and here we are getting it to be rational, we can say that this contradicts the fact that root 5 is irrational. So this contradiction has arisen because of our incorrect assumption that 3 root 5 is rational. So we say that our assumption is incorrect and we will prove the given number 3 plus 2 root 5 is irrational. Now let's move to the third question. So now in third sum we have 3 subdivisions. First one says that prove 1 by root 2 is irrational. Here also we are going to follow the same proof by contradiction method. So we take 1 by root 2 is rational as our assumption. Now when we say 1 by root 2 is rational, then we can also find two integers a and b such that b not equal to 0. In the form of 1 by root 2 is equal to a by b, where a and b are co-primes. Here, to make root 2 as the numerator, we just reciprocate both the sides of the equal to and we get root 2 is equal to b by e. Here again we know that a and b are integers, so this form b by a is rational. If right hand side of the equal to sign is rational, then obviously left hand side of the equal to sign is also rational. Then we will get root 2 is rational. But we know that root 2 is irrational, so this is a contradiction. By proper way we can say that b by a is rational. Since a and b are integers, this implies root 2 is rational. This contradiction has arisen due to the incorrect assumption that 1 by root 2 is rational. So now we will prove the actual required condition that 1 by root 2 is irrational and we say hence proved. Now coming to the second subdivision, it is asked that prove that 7 root 5 is irrational. Here also we are using the method by contradiction, so we take or we assume that 7 root 5 is rational. When we take some number as rational, then we can also find two numbers a and b where b not equal to 0 as integers such that a and b are co-primes. Then we can represent 7 root 5 as 7 root 5 is equal to a by b. When we rearrange this and we take 7 to that side of the equal to sign, we get that root 5 is equal to a by 7b. Since a and b are integers, a by 7b is a rational number. If a by 7b is rational, then we can say that root 5 is also rational. But Since we already know that root 5 is irrational, this is a contradiction. So by this way we give the proof, like here a by 7b is rational as a and b are integers, which implies root 5 is rational. This is a contradiction that has arisen due to our incorrect assumption that 7 root 5 is rational. So we conclude by saying that 7 root 5 is irrational, and the final step we will give in every proof is that hence proved. Now let's move on to the third subdivision of this problem and also the last problem of this exercise. Now in this third subdivision it is asked that prove that 6 plus root 2 is irrational. Again we are going to follow the same method, that is proof by contradiction method. So we assume 6 plus root 2 is rational. When we say a number is rational, we can find two integers a and b such that a and b are integers and are also co-primes, and we can represent the number 6 plus root 2 as a by b. Now taking this 6 to the other side, we get root 2 is equal to a by b minus 6, and by taking LCM we get the form root 2 is equal to a minus 6b by b. Now this part is rational since a and b are integers. If the right hand side of the equation is rational, then obviously the left hand side will also be rational. Then we will get root 2 is rational, but we already know that root 2 is irrational. So this is where the contradiction arises. Now properly putting in the form, we get here a minus 6b by b is rational as a and b are integers, and this implies root 2 is rational. But this is a contradiction due to our incorrect assumption that 6 plus root 2 is rational. Since our assumption is wrong, we can conclude that 6 plus root 2 is irrational, and by this way we are proving the required condition that 6 plus root 2 is irrational. Now this is the last problem of this exercise 1.2, and here we are also completing this chapter. For the people who are using the older editions, the exercise this exercise is named as exercise 1.3, and the exercise 1.4 is also removed. So here we are completing our chapter. So the theory part which we have discussed, like the theorem and the proof of contradiction, proof by the method of contradiction, theories and all, I'll upload in the, or I'll share as post in the Instagram, Facebook and Twitter. You can follow me there and you can take the notes from there. Do subscribe this channel and also click the bell icon so that you don't miss any notifications, and also follow me on the Instagram, Facebook and Twitter, so that you can get the notes of the theory from there. Please continue watching the videos where you are going to get the complete guidance for the upcoming class 10 CBSE board examinations. See you in the next video. Till then, bye bye.